Hey class, so some of you have been asking me about question number 21 on the homework. It's a fun one and a pretty tricky one as well, so I thought I'd make a video for you all. So in this problem, we're given here this radial distance A is given to us. We're given the magnitude of our B field, and as you can see by the x's, we're given the direction as well. And we're also given omega, which is the angular speed at which our crank here is rotating, which drives the rotation or change in position of this arc. Okay, and so we're asked to determine, part A, we're asked to find the frequency. I trust that you guys can find part A, so I'm not going to get into that. But we're also asked in part B to figure out what the amplitude of the EMF induced is. So first of all, it's like, oh boy, howdy, this sounds crazy. We haven't really even talked about amplitudes and things like that, right? Well, all that really means is that the fact that this wire piece is rotating, it's changing the exposed area to the B field, that means that you're going to be having an induced current that is changing with time. And so since it's changing with time, since it's not changing at a constant rate, as you can imagine, if this is moving at a constant speed, the way the area changes is going to vary because, well, you can imagine as it's rotating around that it's moving quickest relative to the B field when it's perpendicular to the B field like it is now, whereas if it's flat across here, its relative motion is going to be smaller when it's coming out of the page. And so anyway, what you'll see, and we'll prove in this if you don't believe me, what you'll see is that your area varies with time, your magnetic flux varies as a function of time, and your change in flux varies with time, and so as a result, the induced current as well as the EMF vary with time. So what you need to do is quantify that and really quantify what the maximum is. So this is where it gets fun and gets a little bit tricky. So if we think to what we've learned, right, our EMF is going to be equal to negative N multiplied by the phi, the change in magnetic flux with respect to time, dt. So that's what we know, and that's what we're going to start with. The question then is, what are all these things equal to? Well, n, I'm guessing you all can guess the value of n. It's just 1 since you have a single loop, right? And then our flux, well, we learned before that flux is the integral of b dot dA. And in this case, our B field is constant and coming out of the page and is always perpendicular to the area created by our loop here, right? So our area, even as our loop changes, the area exposed to the field, even if the loop is down here or down here, the area exposed to the field is constantly perpendicular to that B field. So therefore what we can do is we can rewrite our flux, or well, our change in flux, we can rewrite our whole EMF equation as being equal to negative N is 1, so 1 times anything is just itself, so we can get rid of that. D, and then now we have B times A, and we can just multiply them together since, again, as I mentioned before, they're perpendicular, dt. And as we observe in the problem statement and as implied by the drawing, b is actually a constant value. So since b is a constant value, we can actually pop it out of our derivative, and so what we end up with is that our EMF is going to be equal to negative b dA dt. Oh, that's cool. Sounds good. Well, the question then is what is A as a function of time? We know that it's changing since the thing is rotating, so therefore we must be able to derive A as a function of time. So that's what our next challenge is how can we express A as a function of time? Well, our area really has two parts if we look at this drawing here. All right, so there's some initial area, which you can kind of envision as being this rectangular area here, right? So you have some area there, and so I'm going to call this area A initial, because it seems to be a fixed amount. And then there's this rotating portion up here, right, that varies with time, that's a result of this semicircle. And that's going to vary, right? If, for example, here, it's a half circle that's going to be added to the A initial. And now as it rotates, let's try to envision what it might look like. So after it's rotated, say, 90 degrees, then it's a straight line here. Its area makes no contribution, and your total area is just A initial. And then it rotates another 90 degrees, and now all of a sudden, it's here. And so now its area is actually taking away from the total area. So now the area that you have perpendicular to your field is just this portion. So it's actually, that's when it becomes A initial minus that semicircle. and then it goes back to having no contribution, and then back to adding, and so on and so forth as it continues through its circular motion. So what I can envision from that then is that really our total area must be that initial area plus the contribution from that semicircle. So it's a half circle. Well, the area of a half circle, well, that's just pi r squared, where r, I guess, is just labeled a. So you could write a instead. But pi r squared over 2, since it's a half circle, but then multiplied by some function of time that describes how this is changing. And so as we just were talking about, the contribution of the semicircle really ranges from adding its area, so this function then would need to have a value of 1 initially, and then when it goes to being horizontal, the value goes to 0, and then as it goes to being down here, it's actually taking away that amount of area, so it needs to go to -1, and then it goes back to 0 when it returns to horizontal after going 270 degrees, and then returns to its original position, so it goes back to 1. So you need a function that alters from 0 to 1 to -1 to 0 to 1 to 1 to 0 to -1 to 0 to 1 to 0, so on and so forth. Well, that sounds an awful lot to me like a sine or cosine function. And in fact, since if we define its initial situation as when it's up, contributing completely, you need that function to have a value of 1, so at time t equals 0, cosine would be equal to 1, and so therefore the function that I'm going to use to describe this motion, and seems to describe it accurately, is cosine of whatever angle that semicircle is making with relative to its initial position. Okay, well, that sounds all fun and good, but I said that we need a function that's dependent upon time if we're going to plug it in and use the derivative up here, right? So we need something that depends upon time. Well, I wonder if we can describe our angle with respect to time in some manner that is based on things given to us in the problem statement. And so if you remember back when we learned about circular motion, we learned that theta is equal to theta initial plus omega initial times time plus 1/2 alpha times time squared, where alpha is angular acceleration. Well, in this case, we have an object that's rotating. It does have some initial omega. We can define its initial angular displacement as 0, makes sense. And we're told that its angular acceleration is 0, since we know that the angular velocity is constant. So if that's 0, then what we're left with is that theta is just equal to omega times time, very similar to what we've seen in the past, especially when doing simple harmonic motion and so on. So what you can do now is you can take this, plug it in here for theta, and now you have an equation for the area as a function of time that accurately describes the area that is exposed to the magnetic field. So now you can take this area function, plug it in up here. Oh, I guess it's right there. Almost went past it. All right, plug it in over here, and you should be able to take the derivative and solve for, again, the maximum value is what you're looking for since you're asked to find the amplitude. Best of luck. Hope you guys are able to get the green box of joy, and I'll see you all in class tomorrow. Green box of joy for you.